Hello everyone. Now we are moving on to the part 10, module 4, data communication. So far we were discussing multiplexing, the frequency division multiplexing, wavelength division multiplexing, and TDM, particularly the synchronous time division multiplexing. We covered in detail with problems and everything. Okay, every aspects we covered. Now it's time to discuss the statistical TDM. In last part I discussed limitation of synchronous TDM. Of course it is very clear for everyone the possibility of empty slots. Right now in statistical TDM such inefficiencies are not there, and we will see how it is to be done. So in synchronous TDM, each input has a reserved slot in the output frame, right? So that is making it inefficient because the slot is reserved. If the input line don't have any data to send, or it is having discontinuous data coming, there is no continuous flow. In that case, definitely the slots may be empty in many cases, and that will lead to inefficiencies. And this can be inefficient if some input lines have no data to send. But in the statistical time division multiplexing, slots are dynamically allocated. That is very important. And statistical in the sense we may be using some statistics for determining the bandwidth of the outgoing link and all that we will see. So that is some statistics may involved. Okay. So that is why it is having the name. But mainly the slot allocation is dynamic here. That is something you have to keep in your mind. That is allocated dynamically to improve the bandwidth efficiently. On demand we are allocating the slots, and there is no pre-assigned slot allocation. Okay, there is no reservation of the slots, nothing. On demand, if somebody want to send some data, slot will be allocated and information will be taken from there. So only when an input line has a slot worth of data to send, then only slot will be allocated for it. It is given a slot in the output frame. In statistical multiplexing, the number of slots in each frame is less than the number of input lines. This is something we will see. This is because within a frame, in addition to data, we are storing address information also, because there is no one-to-one correspondence between the slots and the sender. So we have to identify what is the sender from which this information is coming. So because of this address information that is additionally fit into the frame, the number of slots in each frame is typically less than the number of input lines. There is no need, like already in synchronous TDM we discussed, like if there are 5 input lines, there will be 5 slots in the outgoing link. But in statistical TDM it is not like that. It can be less. Okay, because we assume that in all the time all the 5 are not don't want to send the data, or even though if everybody want to send the data, send information, still it can handle. So normally it is taken like less than or equal to. Sometimes if you are making it equal also, then it may be some generalization to what we already learned. Okay, so typically it is we are making this frame as small enough in such a way that if there are n input sources want to send some information, then the number of slots in the TDM frame, statistical TDM frame, will be less than this n. So the multiplexer checks each input line in a round robin fashion, just like in synchronous TDM. 1, 2, 3, like that each input line will be checked in round robin fashion. It allocates the slots for an input line if the line has data to send. But in the previous case, if the line don't have data to send, simply it will keep that slot as empty. But here it is not like that. There is no empty slot at all. Simply if the particular input line wants data to send, then only slot will be allocated. And otherwise it is skips that line and it will check for the next input line. So like that it will proceed. Simply it will tightly pack all information into the frame without any empty slot. In the synchronous TDM, same way, some slots are empty because the corresponding line does not have data to send. Such a situation is not here. In statistical TDM, however, no slot left empty as long as there are data to be sent by any of the input line. Suppose out of n input line only one want to send the data, simply its data will be taken in each frame, maybe multiple slots, and it will be sent. Okay, so that is the idea. But it will check whether other slots want to send the data or not. If no, simply this will be given chance again and again. Okay. So say, now you can visualize like this, it will be more clear for you. This is a pictorial view of synchronous tedium, and this is for statistical tedium. Again, I taken from that Frozen textbook. Some printing mistakes were there. Line A, line B, line C, and this is line D. Okay, that is something overlapped here, and this is line E. So like that, say we have 5 input lines, like A to E. Now from each line, this is a situation of information. From A, we have one unit of information here, but in the next time frame, we don't have data, only this much data. For B, we have data here and here, but C don't want to send any information for the time being, just an example only. Similarly for D, and for E, no data at the beginning, but now we have a data. Same input, you are passing through multiplexer implementing synchronous TDM, and another multiplexer having statistical TDM, and you can see how the TDM frames are generated in each case. Here we have 5 input slot, 5 input sources. So 5 slots are simply reserved or dedicated for all the 5 input sources, and those 5 slots, if they have data, it will be taken, otherwise it will be simply keeping it as empty. Okay, for example here, so this is frame 1, in this is frame 1, this is frame 2. Okay, in frame 1 we have from input line 1, this slot 1 is filled A1 B1, but see, this line C don't have information, so simply we are keeping that slot as empty. Again D1, again the last slot as empty, and this one bit is for synchronization. Okay, the frame synchronization concept that we already learned. Okay, it may be 1 or more bits. Here it is assumed like a 1 bit synchronization. Then we have the next frame. The first slot, no information. Second slot B2 is available. Third slot again no information, because he is not sending data at that point. And next 2 slots D2 and E2 are having information, and again frame synchronization bit. Same thing when it comes to statistical TDM. This concept is clear for you. Now you have to give attention here. In case of statistical TDM, what is happening? As usual, when we are creating the frame, we are taking information from the first input source A1, and additionally we are keeping some address information. That is what makes it mainly different from the other one. Here there is no need of such address information. That is because we are keeping the slots of the frame onto and correspondence with that of the input sources who want to send the data. Okay, so if no data, simply we will keep as empty. And for the receiver also, it know as there are 5 slots, 5 unit of information will be coming, and it will be delivered to 5 receiver destination parts. So that is the thing. See, at the receiver correctly, A1 will be given to destination 1, B1 for destination 2, and destination 3 no data, because this source 3 is not sending any information. Similarly this one. So without any issue, it can correctly split the information because of this empty frames and this reservation. But here it is not like that. Simply if we are keeping information from different lines, how the receiver is going to identify from which line this A1 is coming, and similarly B1 is coming and D1 is coming, because there is no one-to-one correspondence. So that is why you have to identify each input source additionally. Okay, by using some special binary information that identify the source. And normally the normal binary calculation we will be using here, as we have 5 different input lines, to identify a particular input line, 3 bits are enough. A normal binary arithmetic. Okay, 5 sources, 3 bits per input line. And see, those three, using 3-bit, actually 2 raised to 3, 8 combinations, 8 different patterns you can generate, binary pattern. But we need only 5 pattern, remaining 4 pattern, 3 pattern will be wasted. But see, 2 bits are not enough also, because using 2 bits 0001 1011, only 4 pattern you can generate, and you can identify 4 input lines uniquely using 2 bits. But we have 5, that is why we are using 3 bits to identify. Say for the first slot it will be 000, then second slot it will be 001. Like that we can assign address, and we can add those address bits also along with the data. So for A, B1 now C is not there, right? Next we have D1, the information from this fourth one. So we will take its binary 3-bit information that will identify that particular input source here, the path 3-bit address. So this address pattern is coming additionally here, and another one, the synchronization is bit is not needed here, because it is very clear whenever a frame is coming we are containing the actual address of the sender also. So simply this is for sender, coming from sender 1, so deliver it to receiver 1. Similarly this is coming from sender 2, this is from sender 4, 3 is missing. Like that you can correctly deliver the information, so there is no need of frame synchronization bits also. So this is how you can compare synchronous and statistical TDM. So figure in the previous slide shows a major difference between the slots in the synchronous TDM and statistical TDM. And output slot in synchronous TDM is totally occupied by data. In synchronous TDM there is only data, but in statistical TDM a slot needs to carry data as well as address of the destination. In the sense we are actually keeping address of the source. Using this source address correctly, it will be delivered to the address of the receiver, or source or receiver, whatever it is, where it is to be delivered. Okay, if it is some source 1 for the receiver 1, source 2 for receiver 2, if the concept is like that, then accordingly. Otherwise, where it is to be delivered, from information from source line A should be delivered to where, like that also you can maintain address. So that is a normal way how we are maintaining. Destination address we will be providing. Okay. But if the destination and source are in one-to-one correspondence, simply some 3-bit pattern for identifying particular pair of source and destination you can provide. So I think in the previous example I explained like a source address. It is not source address because you are sending the information, right? So destination address we are keeping like that. So now in synchronous TDM there is no need of addressing, right? In synchronous TDM, synchronization and pre-assigned relationship is there between the inputs and the output. That pre-assigned relation, like slot 1 is for source 1 and receiver 1, then slot 2 is for sender 1 and receiver sender 2 and receiver 2, like that there is a one-to-one correspondence, and that pre-assigned slots is what is providing synchronization there. But in statistical TDM there is no fixed relationship between the input and the output, because randomly we are taking data from the input line which is having data at that point. Okay, so you have to identify the source destination address also along with the data where it is to be delivered properly. So and the output, because there are no pre-assigned reserved slot, that concept is not here, because here the idea is to avoid, means eliminate that wastage of space that by empty slot. So that is why we don't have that reserved slot concept. Compared to reservation of slot is actually an easy concept. Simply reserve, and if data, send it, otherwise keep it empty. But here it involves some more complication, like you have to add address and you have to check for emptiness, everything. But you can gain that benefits. You can improve the efficiency provided if all the sources are sending data continuously without any breakage, if everyone will be getting data every time, then it is better to follow synchronous TDM. But this is preferred in a situation where some of the input sources may not have data to send continuously, or they don't want to send some data for some period of time. In that situation, this will be working better. So we need to include address of the receiver inside each slot to show where it is to be delivered correctly inside each slot, because for each slot is given for a source and where that information source is to be delivered. So that information, that destination address also we will keep with each and every source within a frame. And the normal concept of address I already told you. If there are 8 input line, 3 bits, 5 input line, again 3 bits. So how we are getting that? Simply by taking logarithm of 8 to the base 2 is actually log 8 is 2 cube, right? So 3 log 2 to the base 2, which is 1, 3. So log 8 to the base 2 is actually 3. So if you have 8 different input, 3 bits, 4 different inputs, 2 bits. But if it is more than 4 and less than 8, it has to be 3 bit. Okay, because 2 bits are not sufficient, it has to be 3 bit. 3 bits are needed. So that is the idea. So the addressing is in its simplest form can be like this. It will be n bits to define n different output lines. Input line, output line. Normally they are in one-to-one correspondence. So if you have n different capital N different destinations to identify each destination uniquely, log capital N to the base 2, that many bits are needed as the address. That is denoted by small letter n here. For example, if there are 8 different output lines, we need 3 bits to identify each one as our address. Now statistical TDM, some features like what about the slot size, and since a slot carries both data and an address in statistical medium, the ratio of the data size to address size must be reasonable to make the transmission efficient. So this is a very important concept because within a frame along with each slot we are maintaining address also. Imagine a situation where you want only few data to send but your address is more, something like that. Okay, so in that case it is not good. So whenever you are taking a particular frame, you should have to see how what percentage of the frame is actually data and what percentage is address. So what is preferred is the number of bits dedicated for address should be the total number of bits, that is because this address information is actually an overhead, just like the frame synchronization bit. It is actually not what we want to communicate. Simply we are forced to maintain the address to maintain our synchronization. Okay, that is the thing. So always try to maintain the minimum number of bits for the address part and maximum bits for the data part, then it is an efficient scheme. So if you are having a situation where you want send 1 bit per slot and you are maintaining 3 bit as the address, and that is not a good thing. Simply just for sending 1 bit you are wasting 3 bit, because it may be like this: within a frame, one slot, within a slot we will be taking 1 bit of information. Input lines may be many. Okay, such a situation, and maybe some around 8 input lines. So definitely address bits has to be 3 bits. So using the 3 bit you are identifying the address, but the information is just 1 bit. If you are making your allocation like that, that is a highly inefficient allocation, because there is an overhead of 300%, because 3 bits additional, this 3 bit which is the address. In this example only 3 bits, but in general how many bits are totally dedicated for the address, that is actually an overhead. Okay, so that percentage is very high in this case. It should not be allocated like that. So in statistical TDM, a block of data is usually many bytes, while address should be just a few bytes. That is a better strategy. You are allocating only few number of bytes for address altogether, and data is considerably more, very large compared to the total number of bits dedicated for address, so that the overall overhead will be less. Now if you are looking at the frame synchronization bit, again in statistical TDM we don't want this frame synchronization bit. Instead the synchronization achieved by the address bit here. But in other one we need synchronization bit per frame, that is a synchronous TDM, that we see in what is a need for it. We discuss some problems, everything, right? So there is another difference between synchronous and statistical TDM, but this time it is at the frame level, per frame. Already we discussed something at the slot level, now it is at the frame level. If you are looking at slot level, with per slot only data is contained in synchronous TDM. In statistical TDM, per slot we have data and address. That is a kind of overhead. But if you are looking at the frame as a whole, we have a frame overhead in case of synchronous TDM, because per frame we have to identify the beginning of the frame by some special synchronization pattern. That is not needed in statistical TDM, but slot synchronization overhead is there, but frame overhead is not here. The frame in statistical TDM are means need not be synchronized, so we don't need any synchronization bit also, because by default within a frame the slots are synchronized, so we don't need any additional bits for frame synchronization here. Now if you are looking at the bandwidth utilization in statistical TDM, the capacity of the link is normally less than some of the capacities of the each channel. That I already told you. If it is maybe in certain cases it may be equal also, because we are not taking information from all the slots. Simply whoever is having the data we are taking it. Okay, so the capacity can be less accordingly. But normally how we are, because capacity is less in the sense we are considering empty slots also. We just by comparing statistical and synchronous TDM, the synchronous TDM scheme, if you are generating many empty slots, but same situation when you are applying statistical TDM, you can save the empty slot, or you can simply eliminate the empty slot, so that the outgoing link capacity, small capacity, is enough to carry the same amount of information that is being communicated using synchronous TDM. So capacity is less in the sense with respect to the synchronous TDM, that is the thing. So the designer of statistical TDM TDM define the capacity of the link based on the statics of the load for each channel. So how much capacity is to be allocated, that will be determined by some statistics, because previously how many slots are empty, how many are occupied, if all are occupied, like that we will do some study over the past. Okay, by looking at the behavior of information exchange in our previous slot, that we will study, and we will do some statics over that. Accordingly we will determine the capacity of the channel for the next iteration. Okay, so that is why it is having the name statistical TDM. So for example, if on an average x percentage of the input slots are filled, that means remaining is empty. Okay, some actual capacity say 100, only 60% is filled, like that. If x percentage is being filled, the capacity of the link reflects this. Accordingly we will maintain the capacity. Okay, so but of course, if even though this is on an average, because we are taking our static, like on the average x percentage is being filled, but definitely worst case will occur where during peak times the slots may some slots need to be wait, in the sense because they are generating data that is more than that is being handled by the outgoing link. So definitely they have to wait for some time, because based on our previous statics we allocated the capacity, everything, but suddenly due to some reason there is some peak data rate coming, definitely they have to wait. There is no other way. So that about the bandwidth utilization of statistical TDM. Okay, with this we will wind up the concept of statistical TDM. So this much information is enough here, because we saw that synchronous TDM in detail, the working everything, and we find a limitation there, and that is being overcome here. But still we have a overhead related issue here, because of that address some extra bits you have to spend, right? So that was the idea. They may ask you question like explain statistical TDM, or there may be questions like differentiate between synchronous and statistical TDM. We discussed many points and you have to list them. So whenever they are asking any question like compare, differentiate, it is always better to give them like in a list. Simply don't try to write many things. Means just look at the evaluator view, how that person will be evaluating. If you are listing them say into two column, and you are listing this is the plus here, this is how the same concept is handled in this technique, like that. If you are giving some and according to the mark, if it is a 4-mark question, you can give some 4 points that differentiate the synchronous and statistical TDM. That will be sufficient, right? Try to practice like that in a brief and conveying manner. Okay, that's all. With this we will wind up discussion of statistical TDM and the time division multiplexing as a whole, because the two variants we discussed, synchronous and statistical TDM. Okay, thank you.